All right,
Nice.
well, it's our very own Christopher Scaduto with skin exact triangles and equivariant singular instanton theory, fuller theory.
Thanks, Ben. So I'd like to talk about all this. This is work that I've been doing with Ali Daemi for the past year, for 2 years maybe. Hopefully it will be up on the archive in 2 months. So let me just start with some basics. I'll say that links L prime, and L double prime in the 3-sphere form an unoriented Skein triple if they differ only in a small free ball as follows. So L will be this picture. L prime this resolution. This is L. L prime, oops, L double prime is the horizontal resolution. Okay, so the 3 links outside of some small area like this agree, and then they differ in a small free ball, as indicated. And I'm always going to mean throughout this talk unoriented Skein triple, but I'm going to forget this word unoriented quite often, so I'm just going to refer to this as a Skein triple. And one reason I care about these things is because many link homology theories, which have become popular in the past few decades, satisfy some so-called Skein exact triangles with respect to these triples. So many link homology theories I'll just use script H for a generic link homology theory, satisfy a Skein exact triangle, by which I mean that given a Skein triple as above, you have H of L prime, and H of L prime prime. So these will be either vector spaces or abelian groups, depending on how you set up your homology theory. But this is supposed to be an exact triangle, so you have exactness at each vertex. So this is what we mean by a Skein exact triangle. And let me just tell you some examples. This will not be an exhaustive list, but these are kind of what I have in mind when I think of Skein exact triangles. So the first one is Kavanagh homology satisfies such an exact triangle. So this was a link homology theory defined by Kavanagh around 2000, and it follows pretty quickly from the construction that you do have such an exact triangle. Actually, to fit in with the rest of my examples, it's better to take reduced Kavanagh homology, although it doesn't matter which one you take if you want just some exact triangle. The second example, you can take H to be a floor theory for 3 manifolds. So some floor homology defined for 3 manifolds applied to the double branched cover of the link. So the main example here is Haggard floor homology, the hat version, applied to the double branched cover which I'll just indicate by sigma. So this was done by Oshaf and Sapo. In fact, this was done, they were looking for similarities between these two types of theories here. And there are other examples, but that's maybe historically the most important one. And as my last example, most relevant to this talk, you could look for a Floor homology defined directly for links. So the version I'm going to care about is called iNatural. And this is singular Instanton homology. Defined by Kronheimer and Ropka. This particular version around 2010. Okay. But I should also note that all of these examples, I'm going to forget about gradings through much of this talk, but they're there. There's at least some grading everywhere. So the minimal possible grading you look for is a Z-mod 2 grading on everything. So we could at least talk about Euler characteristics. So all of these examples have Z2 gradings. On the appropriate link homology theory such that the Euler characteristic is the determinant of the link. So the Euler characteristic of any one of these link homology theories will give you the determinant. So this is just an integer that you get. Maybe one of the simpler definitions is that it's just the absolute value of the Alexander polynomial, the single variable Alexander polynomial of your link, evaluated at -1. It also has the interpretation as being the size of the first homology of the double branched cover. But it's something you can compute from a diagram of the link. And in this sense, you can also say that the exact triangle that we're looking at for any of these examples categorifies a relation of this form. So the determinant of the link plus or minus determinant of the second link in the Skein triple plus or minus the determinant of the third link, L prime prime. So the signs will depend on your particular Skein triple, but there's always some relation like this, and this Skein triangle is to be viewed as a categorification of that relation. Maybe I should also say here, just to be careful, examples 1 and 2 can be viewed like this. Perhaps also 3, but as far as this whole story goes. Okay, any questions so far?
Examples 8 and phase 2 is always 1. What for not?
That's right. Yeah. So this is true for examples 1 through 2. Yeah. In fact, we'll see from what I say later that what Nikolai said is correct. So the other characteristic of iNatural with the usual Z-mod 2 grading is equal to 1 for a knot. There is another grading on this called the Alexander grading, which can allow you to extract the determinant and get you closer to this relationship. I won't say much about that. Okay. So now I'm going to, because I assume not everyone here knows the details of the theory that I'm most interested in, I'm going to do a brief overview of iNatural and what it means. Okay, and maybe I should say at this point also that my goal will be to kind of enhance the exact triangle story for iNatural. So an important object to begin with is the traceless SU2 character variety of a given length. So I'm going to use the notation, I think that's a math type X. So X of L, which maybe I'll just sometimes call X, is the set of homomorphisms from the fundamental group of the complement of your length to SU2. And the condition you put on those homomorphisms is that they're traceless, by which we mean that if you look at the trace of your homomorphism evaluated on any meridian with the length, you get something traceless. So here mu is any meridian of L, and you mod out this set of representations by an action, which is the conjugation of SU2 acting on your homomorphisms rho. Okay, so there's a special subset of this character variety, which I'll call X red. These are the reducibles. And these are just the homomorphisms in X, such that the image of your homomorphism, which is a subgroup of SU2, is abelian.
So that's sometimes reduced and sometimes reduced.
Sorry?
Yeah. Section red has to be.
Yeah, well, in different theories. This will never be used again, this one. Yeah, maybe I should have something like that. That's common. Okay. Right, so these reducibles, you can easily understand what these are. If you look for abelian representations, they'll factor through the first homology, you can compute all these things. In fact, they have a very geometric description. These are in bijection with quasi orientations of your link. Which are just orientations of L up to the action of reversing all of the orientations of all components. Up to reversing all components. In particular, you can count those. Maybe I should also draw an example of this. make clear what we're talking about here. So this is the hop length. This is one quasi-orientation. Well, it's an orientation, but I care about it up to simultaneously reversing all the orientations on the components. So another quasi-orientation which is distinct from it would be to reverse the orientation on one of them. And those are the only two. So then it's easy to count how many quasi-orientations you have. So the number of reducibles in this character variety, traceless character variety, is the number of quasi-orientations, which is 2 to the number of components minus 1. Okay, and then we can, oh, by the way, here L is the number, brackets here, it's the number of components. And then we can decompose our traceless character variety into the reducibles and the irreducibles. Those are the things which are not reducible, irreducibles. They have irreducible, they have non-abelian image in SU2. Okay, great. So some of the extra structure we consider comes from choosing a base point, or sometimes it's thought of as a framing on the link. I'm going to be very brief about this. So basically what this extra data will give you in terms of the character variety is a preferred meridian. So first of all, maybe you have a preferred base point here, which you're using to compute pi1. And then you also have a preferred meridian around a particular component of your link. And that's all I really mean by this in terms, if we're thinking about things in terms of representations, that's the extra data I mean.
So when you're saying a preferred meridian, you mean you're also choosing a path from P to your component? I mean,
yeah.
You mean there's a different, there could be non-homotopic loops, based loops that, are both meridians, same component of L. Right? And so when you're saying preferred meridian, do you mean a choice of one of those two among those? Or are you just saying in terms of the orientation of which way it goes around? So you are kind of choosing with your quasi with your orientation. I mean, with an orientation on the link and a path from your base point to
that's enough to get.
Then you're choosing what you're calling it.
Yeah, if you have an orientation and kind of a preferred base point that you're computing pi1 with, and a preferred path to how you're going to form your meridian, that's enough to get all this. So in this case, if you have this extra structure, you can define, so let me just say, mu0 here is our distinguished meridian. In pi1, the knot complement, which is really, again, computed with respect to some actual base point here. Then we can define what I'll call x tilde of our link, which will be the representations from pi1 of the link complement such that we still keep the condition that the trace of around all meridians is equal to 0. we add in the condition that around the preferred meridian, so here I should point out that traceless elements of SU2 are all conjugate to a special traceless element, which is the matrix I0, 0 minus I. And around this distinguished meridian, we require that it gets sent to exactly that matrix. And you don't mod out by conjugation. So it's kind of an obvious map from here to X. You just mod out by conjugation. In fact, this has a circle action, where the circle is really to be viewed as the diagonal matrices in SU2, and they're acting by conjugation on these representations here. And you should note that conjugation by diagonal matrices will preserve this condition here, so that's all good. And this is the quotient map with respect to this S1 action. Furthermore, this decomposition into reducibles and irreducibles is really everything to do with this action. So the points that are fixed completely by the circle action are the reducibles, and irreducibles are acted on freely by the circle action. So you can think of this x tilde as the reducibles, right, where the circle action acts trivially, and then for the irreducibles, there's really a free circle orbit for all the irreducibles. Okay, so this is all great. This is pi 1, and this is related to gauge theory because you can interpret these traceless representations as certain singular SU2 connections on the knot complement. So that's why we're looking at this. And so the idea is to do some kind of floor theory, which is related to these character varieties through that correspondence. But in floor theory, what you often have to do, and you have to do it in this case, is you have to introduce some perturbations and some other things to actually make sense of what you're doing. In particular, you have to introduce a perturbation pi, let me just call it pi, which will have an effect on this set. It actually won't do anything to the reducibles, but it will have the effect of turning this set of irreducibles, which a priori might not be anything nice, into a finite set of points. It's something very special about theory. So after introducing this perturbation, and I won't go into details about what this exactly means, but after you perturb things, the irreducibles becomes a finite set of points, and everything else doesn't change. So here's the picture you have.
Chris, before you raise, you got pi natural, that's something defined by compiler.
Yeah.
You are defining CEOs and validity. It's not that different.
Yeah, that's technically.
There's no theorem.
That's true. So I'm giving a description of iNatural, which is, I'll say more about this. The description that I'm giving is not exactly what I'm telling you. It's closely related to what I'm telling you.
But use the same notation.
Yeah. I mean, it is iNatural. It's just not the original definition.
May I ask you why you consider only trace with representation?
Yeah, that's a good question. You don't have to. There are versions of the theory where you what seems to work well is at least fixing the holonomy, or I should say the trace of the representation around meridians to be something specific. It doesn't have to be equal to 0. It can be something else. The technicalities of the theory in the non-trace 0 case are greater. When you get to the floor theory, you have to work over a Novikov ring. There's some technical reasons why you look at this case. It's kind of simpler than the other cases.
So who did those subsets?
Kramer and Rucker.
This other races.
Yeah, if you fix, I mean, they define some versions of Instanton not homology, where you.
But not his.
Oh, that's fair enough. Yeah, I'll say most of this is done in the literature for knots. I'll say how we're getting to links. Okay, so here's the picture we have now.
Just toss it. Chris, just set those over on the table here so we know what you mean.
Yeah, good idea. Okay, so after you introduce a perturbation, this at the circle action space that we're looking at, it becomes a collection of points and a collection of circles. That's because you have the part which really has to do with the reducibles, which was not perturbed. And you have the part which are free orbits on the irreducibles. So given this, I can tell you that phi natural of a link L is roughly a Morse floor homology of a certain Chern-Simons functional. The Chern-Simons functional in the singular gauge theory setting. And also, there's a perturbation flowing around here. But that's roughly what it is. What you should have in mind is that the critical set of this functional is this space that I'm trying to tell you about. So what Ali and I were working on for a while, and we still are, is trying to do all this in an equivariant way with respect to the circle action, to kind of take as much as you can from the structure of this circle action. So you can do all this. In other words, you can do all the floor theory and everything S1 equivariantly. And we have a few papers that go through this, starting from 2019 and continuing. Okay, so let me just tell you what the machine does. So the machine takes a link.
Oh, sorry, another question. If you were to deal with X or texture, another theory, okay, collapse each circle to just
Yeah. So
looking at the Euler characteristics.
yeah, I'll mention that theory as well. Yeah. Right. So the machine takes in a base And here I have to tell you that there's a technical condition on the construction right now that the determinant is not zero. We expect that you can remove this, but this is what we've done everything for.
When you say base link, you mean with the base point and the fixed base
Yeah,
point
like
and the
in
exterior?
terms of this.
So,
Yeah, and I mean, I could have. The important thing is actually you can choose a point around here, and then the rest of this data, I mean, by what I call framing.
so in this condition, the determinant has to do with the fact that when you do resolutions, you can get zero determinant. When you do the Skein resolutions.
Actually, I mean, this condition, it is important there, but I mean, we have this condition here just for purely technical reasons. When we try and construct the floor homology, it's much easier to do it if you assume this. This guarantees that the reducibles. Right, that's basically why. So if this is true, then it tells you the reducibles are kind of, in the gauge theoretic sense, they're cut out transversely already and they're isolated. They're isolated from this. I've written this as a disjoint union, as set theoretic. If this is true, it's true in a greater sense that this is a disjoint union. And this is already cut out transversely, and you only have to perturb this part. So if determinant is zero, you have to do something else to fix things. We have some ideas of doing it, but it's certainly more technical, so we haven't done it. But given such a link, you can then get some algebraic object, which we call an S complex. So this is input and output. And this correspondence is really, it's giving you something up to what we might as well call S homotopy. So it's really, there's a notion of chain homotopy equivalence of such things, and the invariant you get is up to that equivalence.
Does the S stand for Scaduto?
No. Okay, so what?
I'm sure your collaborator did.
right, they're not deep complex. So let me tell you a bit about what an S complex is. So you should just have in mind this picture the whole time, because it's really just up at the chain level. It's this picture. So it's a chain complex, first of all, I should say that. It's a chain complex, but it just has some extra structure which has to do with the circle action. So there's going to be a distinguished sum end over here, which will basically encode all these points, the reducibles. So that's going to have rank 2 to the L minus 1, the number of reducibles, basically the free abelian group on the reducible part. And then the other part of the complex is basically the homology of these circles. So you should really think of this as C of L. Here C of L is going to be what Nikolai mentioned. It's really thinking of things as just the irreducible critical points, not the circles, just collapsing the circles each to a point. And you can form a complex just using that information. But in the S complex, we want to remember those circles. So you're going to see something that looks like this tends to the homology of S1.
But isn't there a degree?
What?
I mean, so for each circle, the degrees are all the same one.
No, there's a degree shift here. The way I've written it here, maybe this is like that. But the important thing is that the degrees of these two copies differ by 1.
But each component can have different degree, or
Yeah, that's right. Yes, sorry. Yeah. I mean, the gradings really come from the floor grading. If you consider each of the irreducible points, and then if you form the circle, they're just stat grading and plus or minus 1, however you set it.
So you basically have to break each circle to maximum.
Yeah, it's another way of
More spots.
viewing it. There's a way of viewing it as you're perturbing the circles to be 2 points. Okay, so the differential has a special form. The important thing about this form is that there are a bunch of zeros in certain spots, and that the differential D, which is really the differential for this complex, the irreducible complex, shows up twice. And you can view all these components here. So all these maps are together the differential d tilde of the total complex. So you can view C tilde of L as a DG module over the homology of S1, which you can then think of as just an exterior algebra over one generator of degree 1, which I'll call chi. Apologize for so many chi's in the talk, but that's another one. Think of chi as like the degree 1 generator of the homology of S1, and you can think of it as acting on this complex. It just moves one copy of C of L to the other. And the important structure here can really be summarized as the fact that the differential anti-commutes with chi, which is just the algebraic version of saying that the complex respects the S1 action.
What is B?
What is what?
B.
Oh, B is, you want the description on floor homology, on the floor
I
complex?
was saying that B is a count of gradients for lines from maximum to minimum. Should be 0, but it's not.
Well, from our viewpoint, V is the map that's it's basically associated to looking at. On the singular locus of the link in S3 cross R, you have a universal complex line bundle, and that map is coming from looking at the using the first term class of that.
Okay, so B doesn't go from maximum to minimum. It goes from maximum of one circle to.
I mean, you could view it that way also.
Between circles, right?
Right, it can go to different circles.
Because within the same circle.
That sounds correct. Okay, great. So this is the algebraic structure we're looking at. And let me just say what you can do with it. Here's a few things you can do with it. The first thing is that you can forget all this S1 action business and just think of this as a chain complex. That amounts to just taking the total homology of the complex. And in this case, you will just get I natural. So as Nikolai pointed out, this is not the original definition of I natural. It's kind of a recasting of I natural. I natural is what you get if you do this circle equivariant construction and then take the total homology, kind of ignoring the circle action at the end.
And the other characteristic of that is signature.
you can see the Euler characteristic of what it should be, because these will all cancel on the Euler characteristic, and you pick up something from here. These are all in the same grading mod 2. So. Okay, great. So that's one thing you can do. There's another thing you can do. You can use the S1 action. And there's a lot to say here, but I'm just going to summarize. So from this S complex, you can kind of algebraically extract things using, this kind of structure that we see over here. You can get, for instance, what we call I from, I to, I bar. These are all ZX modules, so they're modules over a polynomial ring. And they behave in a very similar way to like the knot or link floor homology, the plus minus infinity versions, say Hager floor homology. You can also extract Freushoff type invariants. This leads to a lot of applications to concordance, and there's more stuff you can do. There's a lot of stuff you can do. In our second paper that we wrote on this subject, we kind of explore a lot of what you can do with that. And the third thing, which is really actually kind of part of the first one, is to do what Nikolai mentioned before, to just look at the irreducible homology. And by this I mean, you just focus on this complex just showing up here. So we call this I out. And it's just the homology of the complex whose underlying generators are the irreducible things from the character variety. Now this theory is very interesting for a number of reasons. Let me tell you why. So one thing is that the Euler characteristic of this theory is equal to 2 to the number of components minus 2 times the Murasugi signature of the length. So this is just an integer. You can define it by taking the average over all quasi-orientations of the oriented or quasi-oriented signatures of your link. So for knots, these things don't matter. There's only one quasi-orientation for a knot, and there's only one signature. For a link, you can consider oriented signatures. They only depend on quasi-orientation. And to get something which doesn't depend on orientations or quasi-orientations, you can take the average and you get what's called a Murasugi signature. And so this irreducible homology is thought of as categorification of a multiple of that Murasugi signature.
So for knots, this should follow from excess Lin's paper.
Yeah, so this is
for links of more components.
Right, so this is this work of Lin and Harold, which predates what I'm talking about. They computed that if you count the traceless SU2 representations for a knot in some way, they did it in different ways, but they should be the same. You would get a multiple of the signature of the knot. I stated something for links, and it also has a floor theory here, but it's closely related to.
So who proved that for links?
We did. We're going to use the exact tract.
No?
But I think you're right that you could also just probably use the argument. You gotta
you need to
certainly
match the
Yeah, you have to match some things up. I should also mention this theory has an antecedent due to well, there's an earlier version of this due to Collin's theorem. I should also mention their names. So we define this theory, but I wouldn't say that it was kind of already defined. In some version of it was already.
It's not the same.
It's not the same, you said? It's not the same construction, you mean? You don't think it's the same
Construction
theory?
was kind of complicated.
I think
Yours corresponds to double branched covers, and theirs corresponds to quadruple branched covers or something.
I think if you tweak, you might be right with the specifics.
You need to tweak.
There's a version of what I'll just say that. Okay, so the other interesting thing about this, if that's not enough, is that it's not clear what, I mean, I should say that I natural, which is just the total homology of this complex, is conjecturally the same as, say, H of K hat. So there's a version of the Hagar homology, or maybe this is for knots at least, maybe I have to modify it for links. Conjectured by Kronheimer and Mopka that these are basically the same theory after you compute them. So I'm interested in things that aren't quite obvious to see from the other side of the world in Hagar land. And one thing is this irreducible Instanton homology. So it's not at all clear if there's an analog of this theory in other Floor theories. There's certainly none that I know of, and there's a question of whether you can extract such an invariant, such a Floor homology from those other Floor theories that does categorify the signature. You might have it in cyber branch theory. Or double branch covers.
You do double branch cover and you do cyber.
That's that the Euler characteristic is a multiple of the signature.
I need to go back to the paper. I think that's what it is.
We should go back. Yes, I mean,
There is definitely more Murasaki signature.
for a secret signature shows up there, I believe that. Okay, and here I'm getting to the main point of what I want to get to, which is what about exact triangles? So what about a Skein exact triangle for C tilde is S complex? But you could ask the simpler question of what about even for this irreducible theory? That seems interesting. We get some kind of Skein exact triangle for this theory, which, as far as I know, isn't looking like some of the other theories. Let me just give an example, a very simple example of how you might approach this. So in this picture, if you insert this here, this would give you a link L, which is a hop link. And if you put in the other two Skein pictures, so the next one would be this thing, and then this thing. This would be what I call the L prime. This would give you the trefoil, right-handed trefoil. and this other thing would give you an unknown. So you have a Skein exact triangle. I'm sorry, you have a Skein triple, not a triangle, which I'll just write it like this, involves the half length, the trefoil, and the unknot. These are just links. And if you look at this irreducible theory applied to them, remember, the irreducible Instanton homology of a link basically at the lowest level of interpretation is counting the irreducible traceless SU2 representations. The fundamental group of the complement of the half link is abelian. There are no irreducibles. Same with the unknot. That's abelian. Well, you can find one for the trefoil. So this is C. Okay. So this is not exact. But you could see this. I don't have to write down a floor homology triangle to even see this. You could see the failure at the level of what would be the order characteristics. That's actually explaining why you would not have an exact triangle. The Morisugi signatures for these two are 0, and for this one it's the not signature -2. It's equal to -1 because it's in factor 2. So let me explain what we can do. So the naive thing doesn't work. Let me tell you what does work. So there's one main algebraic construction. For an S complex C tilde, not necessarily coming from a link, you can define what's called its suspension. And I'll call it sigma C tilde. So this type of construction already appears in Ollie's work with Mike Miller-Eismeyer. So we're doing something similar. And at the simplest description of this is that it's the tensor product of your S complex with another very simple atomic but non-trivial S complex. This S complex O tilde, the irreducible homology is rank 1. The reducible part is also rank 1, and there's only one part of the differential which is non-trivial. It's what I call the map delta 1. Everything else in the differential d tilde is 0. So this is what we mean by suspension, and it will show up in a second. The other thing I need to tell you is if you do have a Skein triple, which I'll write like this, there's some numerical quantities we can define. So given two consecutive links in the Skein triple, choose orientations that make the resolution connecting them an oriented resolution. So you want to choose these so the resolution is oriented. Then we define this quantity epsilon L prime to be the signature of L with respect to this orientation, so it's the oriented signature, minus the other one. And that's actually well defined, independent of your choice of orientations, as long as they kind of satisfy what I said here. The orientations on the components not involved in the resolution should kind of match up. And now let me give you the main theorem. They got the year. It was proved last year. Writing, right? So if we have a Skein triple, and I'm going to assume that, so whenever you have any Skein triple, one of the links has one more component than the other two. You're going to assume that that's L. So without loss of generality, we can assume that. And I'm just going to abbreviate C tilde for each link in the natural way. Then we have 3 exact triangles. Let me put this exact triangles in quotes. The 3 cases depend on the values of that invariant. I told you they're epsilon. It depends on how the signature is behaving under your Skein resolution. So if I put your epsilon L L prime and epsilon L prime prime L, depending on, oh, by the way, I should throw in this condition. Determinants are all non-zero. There's some version of this surely without this condition, but it's not exactly this. We haven't done it yet. So they all have determinant non-zero. If these epsilon invariants, by the way, epsilon always lives in 0 plus or minus 1. And if everything has non-zero determinant, in fact, you can rule out 0. Epsilon is always plus or minus 1. If you get 1 and 1, you have the naive version of the exact triangle. If you have minus 1 and 1, you don't get the naive exact triangle. You have to use this algebraic operation of suspension at one of the vertices on one of the S complexes. So in this case, it's here. And there's one last possibility. Part of the statement is that these are the only 3 possibilities. In the last possibility, you have to do, there's a version of negative suspension. And that's the last possibility. In fact, these 2 cases are related by mirroring. If you have a Skein triple of links, which is in this case, if you took the mirror of all 3 links, you would be in the other case.
So these are exact triangles at the level of chain complex.
Right, so that's why, yeah, so I wanted to say something about what we mean by exact triangles. We mean this in kind of the appropriate sense of on the chain level. So if you're familiar with the triangle detection lemma, you can take that as the definition of exact triangle. But one consequence is that any of the vertices is homotopy equivalent to the mapping common. So I think I'm out of time. So I think I'll stop here.
Any questions?